Nice to see everybody after the midterm. Okay, so I think the midterm was pretty okay. Uh, Similar to I think past concepts that we have. I mean, all the concepts we have covered. Of course, the style of some of the questions were a bit different, but the concepts were still the same. All right. So if you have anything that you want to clarify, you can always email me. Okay. If you're not sure why the answer is as such. Okay. So we are nearing the last few sections of the module already. All right. So last before the midterm, we covered on Mutex. Okay. So today, what we're going to do is going to be fairly a bit more relaxing. Okay. We're going to just finish up on the topic on semaphores, and then I'm going to spend some time to look at the demo of the semaphore and see what happens on the board. Okay, and then we'll just go through one more set of slides to understand some of the issues and challenges with dealing with multi-threaded code. Okay, things like deadlock, priority inversion, and so on. Okay, so we will be looking at that today, and after that, I will open up for any questions that you all have regarding the project or the final assessment. Okay, so let's get started. Okay, so this is where we left off last. Okay, the discussion on the mutex. All right, so I hope you have tried the lab, okay, to see how it behaves and understand what is happening. Okay, so in mutex, basically what we saw was a way in which we can protect access to shared resources. All right, and it helps us to ensure that there is no form of data corruption happening, all right, in the event that a threat that is accessing a shared resource gets preempted. Okay, uh, the important rule, like what I demonstrated last lesson, was the idea that a mutex is tied to some shared data is only within the programmer's mind. Okay, so only you know why you created the mutex. Okay, so when you are dealing with shared data, okay, this is of course critical when it is a big project where many developers are working on it, where you have a lot of shared buffers, shared resources, shared peripherals, and so on. So everybody in the team should sort of reference a document to know exactly how to use these shared resources. Is there a semaphore tied to it? Is there a mutex tied to it, and so on? All right, so that everybody who is using these shared resources are able to follow the rules. Okay, because if you do not follow the rules, the OS cannot catch you for that. Okay, the OS will behave according to the rules of how you use its kernel services. So if I create a mutex, if I say a lock and it's not available, it will just block the task. But if I try to access the resource without using the mutex, it will still grant you anyway. Okay, because it does not link the mutex to the resource. Only you know the link between the mutex and the resource. Okay, so it's always important to have proper documentation, okay, especially in a big team project, okay, of all the shared resources and what are the rules of engaging these shared resources. Okay, so now we are moving on to another thing, another important kernel sort of service by the OS, which is the semaphore. All right, so a semaphore, in a sense, it is in some ways can be used like a mutex, but it's actually more versatile. All right, so a semaphore, you can think of it as a container for a specific number of tokens, where a token is uh, sort of related to a particular resource. Okay, so for example, your KL25Z bot. Okay, so your KL25Z bot, let's assume that, okay, for now, maybe I have 2 ADC channels. Okay, so just assume that I only have 2 ADC channels. All right, and I may have to multiplex this to different sort of sensors or peripheral devices to do the A to D operation. Correct. So maybe one is a IR sensor here, Okay, the other is a temperature sensor here, and so on. So there's a lot of sensors, and for each of these sensors, I have a specific task. Okay, TIR, TTemp, and so on. So I have a specific task written to manage these activities, which are tied to an ADC, which is also shared. So when I write my code, okay, when TIR is running, it may not be for sure, correct? You can't say for sure that that ADC module is available, correct? Because maybe the temperature sensor module is currently, or the task is running and is using the ADC module to perform some activity, correct? So I must first check whether the ADC module is available for me to use. Okay, so to do that is where semaphores can come in. So since I have two ADC modules, all right, I can say that these two ADC modules can be shared across all these six different, okay, all these six different peripheral sensors. So when I try to acquire, or when I want to do the ADC operation, I must first access the resource. That means I must acquire the resource by taking a semaphore. Okay, so if I get the semaphore, then I know that I have gotten the resource. All right. So of course, in your code, you must manage which resource is available. Correct. So since I have two ADC channels or two ADC blocks here, in your code, you need to manually manage this hardware resource to know which one is available, which one is taken, and so on. Okay, so that one the OS will not do, but the OS can help you to keep track of edit at a higher level. That means at the OS level. So what we can say is when the TIR or T temperature sensor or T distance sensor or something, okay, whenever any of them want to do ADC operation, they must first acquire a resource. All right. So when they acquire the resource, then they know that, okay, out of the two ADC channels, one is available for me to use. So I can carry on with my ADC operation. And once my ADC operation is done, I can release the resource. So some other task that is also wanting to use this ADC block can do it. Okay, so that is a way of managing the hardware resources or any other resources, okay, at your task level. Okay, so the reason why you want to do this at the OS level is because when the resource is not available, you can automatically block the task until it is available. And the OS will manage this for us, correct? And the OS will automatically put that task back to a ready state once that resource has been released by another task. Okay, so that is where the semaphore comes in to manage resources that we have. All right, so in terms of semaphore, there are a few different terminologies that you might come across in different books or online material. Okay, so one of the common ones, they call it P and B. Okay, so P is basically to take. So in some books, okay, you may say they might reference it as Sam take, okay, and Sam give. Okay, or in other cases, it might be Sam pen, okay, and Sam post. Okay, so or another common terminology is Sam acquire, okay, and Sam release. Okay, so different OS or they might use different terms, but they all refer to the same thing. One is to take the semaphore. That means you want this resource, and then after you finish, you release the resource. So of course, when you want to take the semaphore, it must be available. So you first check whether the count is greater than 0. So if the count is greater than 0, the semaphore is available. So what you can do is you can acquire the resource by decrementing the count. Okay, so there's a question here. Okay, so if Semaphore manage resources at task OS level, Mutex manage resources at what level? Okay, so both of them are at the same level. That means we are all talking about managing the code or the shared resources at the same OS level. Okay, the reason why we want to use these OS based services instead of using your own approach is when you use the OS services, when that event or when the resource is not available, the OS allows us to automatically block the task. Correct. Okay, let me give you an example here. Okay, let's say we go back to this idea of Mutex. Okay, let's say we go back to the idea of Mutex. Now, instead of Mutex lock and Mutex unlock, you can say that why bother with Mutex? Correct. It's easy. I can just create a global flag. Correct. I can just create a global flag. Okay, global variable. Okay, and then I just say is available. Okay, then I can just check whether if available. Okay, and then do something. If not, do something else. Then same thing over here. If available, do something. If not, do something else. So you can do all this data protection on your own without the OS also. Correct. That means you can create a global variable and do these checks. It will still work. But what's the difference? The difference is if you do it your own way without making use of the OS, then you're not fully utilizing what the OS is able to do for you. What is the OS able to do for you? The OS is able to free up CPU resources and allocate them as and when tasks need them or don't need them. Correct. If I use my normal approach here, I create a global flag and then I check it across different tasks to manage a shared resource and things like that. Then how do you go back and check again? Correct. When is the next time it's available? Correct. So you need to keep running your code to know whether it's available, it's not available, and things like that. Whereas if I make use of the OS to manage it for me, then that whole thing is taken care of at the back end for me. All right, because the moment if I try to lock the mutex, it is not available, then my task is blocked. When the mutex becomes available, the OS manages it to take responsibility to change my task back to the ready state, and eventually I will run and I can do what I want to do. Okay, so the idea is these tools allow us to more effectively make use of the CPU and create a nice, more comprehensive multi-threaded code base. All right, so that is the thing you must shift towards. So when you use Mutex, when you use Semaphore, and later on message queues and so on, the thought process of writing your code should change. All right, so whatever that we have learned before in terms of single-threaded environment, global variables, interrupts, okay, so some of them still apply, but the way we design our code base, the way we architect how we are going to manage the different activities of the system can now change to make full use of the OS that is available. Okay, so the same thing over here. All right, so in this case, when the Semaphore wants the resource, you can use your traditional flag-based approach and still solve it, but then you still need to go back and keep checking. Correct. But now with Semaphores, what happens is the management of the task to know whether it should carry on or it should wait is done for us by the OS. We just focus on writing the code on what to do if once I get the resource. So in this case, the P is to take the semaphore. So once I take the semaphore, I will decrement, correct? So just like, for example, in this case, if my original ADC, okay, if I have a semaphore ADC, I will say my initial count is 2 because I have 2 ADC blocks. Correct. So the moment one is taken, I have to decrement the value and I return. All right. But if when I try to take, the count is already 0, okay, then I need to join the queue. That means I need to wait for my turn to get the semaphore, and I'll go to a block state. All right, so eventually when somebody or some other task releases that resource, the OS will change my status from block to ready, and then at some point of time, the scheduler will change me to the run state. Okay, and then I can carry on. Okay, and so that is semtake. Now is semgive or sempost. So once you have acquired the semaphore, you finish using it. All right, you can release the semaphore. So when you release the semaphore, you increment the value by 1. Okay, and when you increment the semaphore and you release it, all right, what happens is the OS will know if any other task has been blocked and waiting in the queue. All right. So once it knows that some other task has been blocked and is waiting in the queue, it will automatically move that task into the ready state. Okay, and then you will get a chance to run. Okay, because now the semaphore has been allocated to that particular task. Okay, so let's look at this example. Okay, then we get a better idea. So in this example, we have 3 resources as is equals to 3. All right. So initially a task comes in, it acquires a semaphore, so it becomes 2. Another task comes in, becomes 1. And then the task that was originally using it releases it. Correct. So a task that acquired it releases it, so it is done with the resource, so the count increments by 1. So another task comes in, takes it 1 0. So at this point of time, what happens? At this point of time, there are no more resources available in the system. All right. So when a task comes in, all right, and tries to acquire this resource, okay, it will now go to a block state. So X is now going to join the queue waiting, all right, for the semaphore. Next is process Y. So another task also comes in and it also wants a semaphore. So it is also blocked and is put in the queue. Okay, so now there are 2 tasks waiting in the queue and they are both blocked because there are no resources available. Now eventually one task releases the resource. Okay, so this task that acquired it has released the resource. So what happens? Okay, so you can see that when I release the resource, the count actually doesn't change because the moment the resource is released, it is automatically allocated to to the task that was waiting, which was the process X. Okay, so that S is still 0 after the last task releases the resource. Okay, then again when another task release, so when this task release the resource, okay, again the count is still 0 because there is still one more task in the queue. Okay, so the moment one resource is released, the OS automatically allocates this resource to the task in the queue, which is process Y, and Y gets unblocked. So now there are no more tasks waiting in the queue. So subsequent release of resources will have to increment the count. Okay, so that is basically how the OS will actually help us to manage these resources. So the semaphore is the idea, right? The idea of managing multiple resources. How we want to use it, in what context, is up to us to decide. Okay, so later in the lab, we will look at an example where we use semaphore for resource management. And at the same time, semaphore also has another useful feature, which is it can also be used to synchronize some tasks. Okay, so to synchronize tasks, for example, your robot, correct? You can say that when my robot runs after 5 seconds or after a certain distance, then I want the LED to light up. Okay, or after some activity, then I switch on the buzzer. All right, so how do you synchronize the actions of one task with another task? Okay, so there are many different ways of doing it, which we will learn in other lectures. In today's class, we will learn how semaphores can also do it. Okay, so in terms of semaphore routines, first we need to create a semaphore. So that is done by calling OS semaphore new. So when you create a new semaphore, you need to initialize the max count and initial count. Okay, so if you look at this example over here, the max count is 1, okay, and the initial count is also 1. Okay, so when a max count is 1 and initial count is 1, so the semaphore can only take 2 values, 1 or 0. Okay, 1 or 0. So in essence, a semaphore like this is what we call a binary semaphore. And a binary semaphore, you can say that it behaves in a similar fashion to mutex. Correct? Because mutex also has the same concept where it is either available or not available. Correct? 1 or 0. So the same thing applies here. Okay. Now to use the semaphore, So in this example, which I'll demonstrate later, you can acquire the semaphore, okay, before accessing a shared resource or accessing any resource. So in this case, this resource is the LED. Okay, so I'm using it in a very similar context to how we use the Mutex. All right, so before I acquire the LED as the resource, I must first take the semaphore, and after that, I release the semaphore once I'm done with the LED. Similarly, over here, I acquire and then I release. Okay, so these are the ways in which you can use the semaphore. Later, I'll show you another way for the synchronization part. All right, now, so there is also another aspect. So in the mutex, all right, there is also the idea of mutex with no weight. All right, that means what do you do if you try to acquire the mutex and you don't get the mutex? Similarly, you can also have the same situation here where instead of OS wait forever, you can say 0 in case of no timeout. Okay, so these are options that we have. Now the question then comes, what do I do if I put 0? Okay, so if I say OS semaphore acquire MySem 0, okay, instead of OS wait forever, then what happens? That means when I come to this line over here, I need to know whether I really got the semaphore, I didn't get the semaphore. All right, and the only way I can know is I must always check back with my return status value. Okay, so that is something that you can try, okay, in the lab, okay, or at home with the board. You can see that all our calls or kernel calls actually have a OS status T. Okay, so in the tutorial also, I think I have given a discussion on this. So it is always good practice to check whether the status is okay or not okay. Okay, you just need to check whether it's okay or not. Okay, in terms of error messages, there can be a lot of different error messages. So as long as it is not okay, that means it is in some error state. All right, so then your code must now take into consideration that I can be executing this code with the semaphore or without the semaphore. So what should I do? So you have if else statements and so on. Okay, so that makes your code a bit more complex, correct? Because now you need to factor in two possible scenarios, correct? What to do if I get the semaphore, what to do if I don't get the semaphore. Okay, so it's all up to you how you want to design your architecture. All right, of course, the OS wait forever is easier, a more predictable approach because I will know that I will only carry on if the resource is available. So I don't need to worry about the case where the resource is not available. Okay, so that is the more preferred approach. But if your scenario or your application requires you to execute this code or some part of this code either way, then maybe you want to put a timeout of 0 and then put some if else statements in the rest of your code to factor in what to do for the two different cases. Okay, so this is one thing that you should take note of, whether you want a timeout of 0 or wait forever. Okay, now mutex versus semaphore. Now, the concept of semaphore is again, though we use it as a means to protect or gain access to resources, you can also use it as a way to signal between one task to another task or from interrupt to another task. Okay, so that is what we will be looking at later. Whereas mutex, you don't use it for anything else other than to provide mutual access, mutually exclusive access to a shared object. Okay, the concept that it is similar to a binary semaphore is true. Okay, because if I create a semaphore with a binary with a count of 1, all right, then it behaves like a mutex as well. Correct, but okay, there are some changes, and one of the important changes is differences is that mutex has a built-in priority inheritance mechanism, which we will cover later. Okay, and this is important, okay, in cases where you have access to shared resources between high priority and low priority tasks. Okay, so this priority inheritance I will cover later in the next chapter, but for now That is a key difference between a mutex and a binary semaphore. Okay, so one of the common things that people will think is that, okay, Semaphore handles several copies of equivalent resources, whereas Mutex handles one. Okay, so Mutex is, again, you think of it more of not resource management, but more of protecting the resource. Okay, so it's not about trying to acquire whether the resource is available and then I want to take it. No, that is the Semaphore use case. The Mutex is this resource is now shared, okay, between multiple tasks. So I want to ensure that when one task is using it, another task does not have any access in between. All right, so the concept of use is a bit different. Okay, mutex is to protect a shared resource, whereas semaphore is I have shared resources, okay, but multiple tasks need to acquire that resource before they can use it. Okay, another thing is semaphores do not keep track of the order of access, so it treats all the resources identically. Okay, so in the earlier example, okay, when I created two ADC module, it does not differentiate between the two ADC modules. I mean, in terms of the software implementation. So if I say I create a semaphore, okay, my sem, okay, I call it ADC, then the way I use a semaphore, it will not differentiate whether it is resource one or resource two. Okay, it will treat both of them as equal. Okay, so that is the way the OS behaves. Of course, how we manage the two different resources with the semaphore is up to us to decide. All right, so once the resource is acquired in terms of the semaphore, then in your code wise, you need to know which module is available. Is it ADC module 1 or is it ADC module 2? Okay, and then that module should now be allocated to the actual task that wants to use the ADC. Okay, so now let's look at one of the issues, all right, in multi-threaded systems. Okay, and one of it is what we call a deadlock. Okay, so in a deadlock, what happens? Where everybody is waiting for someone else to finish. Okay, and then because everybody is in a waiting state, then eventually nobody wants to give up the resources. Okay, so everybody cannot carry on. Okay, so for example, is this where process one, okay, requires or is holding on to resource A. Okay, so it is already acquired resource A. So maybe I draw a timeline here. So process one and process two. Okay, so if you look at it in a timeline, what happens? Process one is running and then it acquires, okay, resource A. All right, then at some point of time, maybe there's a context switch, okay, and process two can run. And when process two runs, it acquires resource B. Okay, and after a while, maybe there's another context switch back to process one. And when process one is running, again, process one is running, it tries to acquire resource B. So what happened? Resource B is already acquired by process 2, correct? So it will not get it. Okay, so it will not get it. So it'll go to a block state. And then process 2 runs. And process 2 tries to acquire resource A. And what will happen? Resource A is already held by process 1. So this also cannot work. So it will become blocked. So what will happen? So from this point of time onwards, both of them are blocked indefinitely. Because both of them is holding on to one resource and they want another resource that is held by another task, and both of them don't want to give up the resource. Okay, so this is what you call a circular wait or circular dependency. All right, so when this kind of things happen, then you cause a deadlock. Okay, when both the tasks cannot run. Okay, so how can we resolve this? Okay, how can we resolve this? So there, of course, there are a lot of different approaches that you can take. Okay, but one simple way to resolve a deadlock is you acquire resources. Okay, you acquire shared resources in same order. Okay, so if now we change this and say that since process 1 and process 2 both require resource 1 and resource 2. Okay, so process 1 and process 2 both require resource A and resource B. So when process 1 is running, the same thing happens. I require resource A, and then after that I switch to process 2, and process 2 must also follow the same order. So the process 2 must also try to take resource A, so it will get blocked. So you'll be able to switch back to process 1, and process 1 can carry on. Okay, so by just a simple change, okay, by ensuring that all the resources are acquired in the same order, shared resources are acquired in the same order, then any other task will also have to follow the same order. So whichever task that took the first resource will automatically get the chance to finish up first and then release the resources for the next task to carry on. Okay, so this is one very simple way that you can implement yourself in code, all right, to solve this. Okay, of course, one of the advantages now is with improvements in software and compilers. There are advanced compilers that can actually analyze your code and preemptively warn you that there are maybe potential deadlock situations with the way the code is written. Okay, so software can also help to catch some of these situations in case we miss out. All right, so that is again one of the things that we need to be careful about when we have shared resources among different processes. Okay, so that brings us to the end of this set of slides. Okay, so before we move on to the next set of slides, two things. If you have been enjoying this module, all right, and you think you are interested in being a TA, I will send out a Google form sometime next week, okay, for you to fill in the details. All right. For some reason, I always get many people. I think last batch I about 20 people sign up to become TAs. All right, but at most I can take maybe 4, okay, depending on the class size. Okay, so at most maybe 4 or maximum 5. All right, that I might be able to take for TA. So if you're interested, okay, I will send out the Google form, and you can submit your interest there, and then when the exams are all over and everything, then we can look through and I will contact you. Okay, so now let's look at the okay, so maybe before you go on to the lab, okay, maybe I will go to the next set of slides first, and then we'll go on to look at the lab demo for the Semaphores. Okay. Okay, so this set of slides are fairly easy. Okay, just a few concepts only for us to understand. All right, and some revision on the scheduling and the RTOS as well. All right, so we are just going to take a step back, okay, to reflect upon why we are going in this direction, okay, compared with the super loop, okay, and just a review of some of the issues with the RTOS. Okay, so as you have said before, the whole idea of RTOS is to meet very harsh or very strict timing constraints that the system might have. Okay, and is widely used in many industrial, commercial, or even personal applications. All right, so it is a very good skill set for you to have, okay, for you to update on your LinkedIn profile, okay, the moment the module finishes. All right, okay, to say that you are an expert in RTOS. Okay, so it's a value add, especially as a computer engineer, to have this skill set. Okay, and even though we expose you to this particular OS, once you're familiar with one OS, it's easy to just apply it across all different OS. Okay, it's almost the same. All right, of course there will be differences with some of the behavior, of one OS with another OS, but generally those are things that you can easily pick up and sort of know how to change your code. Okay, so again, why we want OS on embedded systems is basically to ensure that we do not have a very big loop, where you are trying to do one activity, function 1, function 2, function 3, and so on, and then you have so many interrupts. Okay, so interrupts help us uh, to handle a lot of these time critical events. There's also a limit to how many interrupts your system might have, and sometimes uh, if you have nested interrupts and so on, that can also add some unpredictability to the response. Okay, so by introducing an RTOS, okay, you can actually help to streamline the whole problem into a set of tasks, and then you focus on each task separately. Okay, so of course, uh, as good as RTOS is, it's always good to remember that in some cases it's better not to have an RTOS. Okay, so in some cases, if your system is not something that is going to scale over time, the requirements are fixed, okay, and it can be done with just your loop and your interrupts and your function calls and so on, then just stick with it. All right, so it's not necessary to put in an OS just for the sake of putting in an OS. All right, unless you feel that the complexity is something that can benefit with an OS. All right, then you go in this direction. All right, so if you look back at what we did, okay, in the first few slides about the GPS based system, all right, so you can see that this was an issue, correct? Because you have different tasks, correct, and each of them can have different amounts of execution time, and at the same time, all right, there is a issue of responsiveness, correct? Because if the GPS data comes in after I finish the decode, then I need to wait for the next round of the decode to run before I can get the updated position. So all of these are genuine issues which warrant that it is better to go in the direction of OS. All right. So in this case, instead of writing it this way, okay, I can change it, okay, to say that I have one task for decode, one task for check, okay, one task for record, and so on. So I have multiple tasks, okay, and of course these different tasks will have access to different shared resources, okay, and then I must manage them with semaphores, mutex, and other things that we're going to learn. All right, so now when you think of this problem and you try to look back at what we have studied so far, you can see that I don't need to do it function by function. I now break it up and focus on each problem separately, correct? So one task to just handle decode, one task to just the checking, one task for the recording, then I have switch and LCD and so on. So it now becomes easier to focus on specific tasks and then look at how are they going to communicate. So I need to put in mechanisms in place to send data from one task to another task, to synchronize, correct? One task should only carry on after the previous task has finished. So for example, t-check. T-check doesn't need to run unless a new data has come in, correct? So the T decode will be the first to be triggered, all right, when a new GPS data arrives, and only when decode has been triggered, then I let the check task to come and check against the database, correct? And while the checking is going on, I can do recording in parallel, correct? Because recording is making use of the same data as T decode. Okay, it's a new updated recording that is there. So part of the recording can also start while the T check is going on. And once the T check finalizes where there is a new pothole discovered, then the T record can also update some new information. Okay, so you can change the way you write your code, the way you think about the problem when you switch from the single threaded approach to the multi-threaded approach. Okay, so that is the key idea here. So in terms of RTX, again, these are just some basic information. So it's compatible with a wide range of ARM cores. So if you are dealing with other ARM-based processors later on, you can still load RTX onto it and you can still run. Okay, in the very first lecture, I also talked to you about the Mbat Os. Okay, so the Mbat Os is also another free open source OS that is compatible with our board. All right, so that is also something you can play around with, okay, once the module is over, and you can try out that particular style of programming as well. Okay, so in terms of the library, okay, so we are making use mostly of the RTX kernel, okay, which uh, provides us with the scheduling, the framework for the Mutex, the Semaphore, and everything. Okay, so of course, when you talk about RTX kernel, it also provides us with a whole uh, runtime library to do a lot of other complex stuff as well. So if your project that you're going to be working on requires USB device interfacing, flash system, networking, and so on. So these are also things that are supported in the library. All right, but for our use case, the basic kernel is what we are using to come up with architecture. And in terms of the library, we are going to be developing our own libraries to control, or you have already been developing your own libraries to control all the various subsystems. Okay, so in terms of the source code of RTX, all right, if you open up the folders, you can actually see the full source code. So it is uh, there for you to actually see and to understand actually how they have actually created all these lower level OS based libraries. Okay, but of course we do not need to go into that because we are using it from the application perspective. Okay, so creation and deletion, I think we have talked about this before already. Okay, the task control block, the stack, and so on. Okay, so when you create the task itself has a context. So the context is a copy of the entire memory of the stack information, the registers, everything that the task was doing at that point of time. And whenever you are having a context switch, okay, between one task to another task, okay, then you need to save the current state onto the context and then switch to the next context. I mean, switch to the next task. So when you switch to the next task, that current last save context will be reloaded, okay, for it to carry on. So that is how it is able to know exactly where it left off and where to carry on from. Okay, so that is the context switching. So this is actually happening very, very fast in the background for us. Okay, so but when we write the code, we do not worry about this because this is handled by the OS. We just focus on what each task should do. All right, so as long as we are aware that even though we write the code in a way that we expect task A to run fully and task B to run fully, and we think that it owns the CPU, but it's actually sharing the CPU, correct? And at the same time, since we also know that this context switching is always happening in the background, we need to put in that precaution to protect the resources and the memory, okay, to ensure that if another task tries to take uh, a shared resource, then and we are in the midst of using it, it should be blocked. Okay, so these are things that the OS helps us to manage because all this context switching is always happening in the background. Okay, so in terms of scheduling, all right, so we saw some different scheduling algorithms in the past, okay, in the lecture. So in our case, the RTX is using what we call the prioritized scheduling. Okay, so in prioritized scheduling, that means the tasks with the highest priority will be dispatched first, all right, and then the other tasks will be in the queue. All right, so the whole idea is the real-time response that we want. So when we already allocate a higher priority to a task, that means we are telling the OS that this task needs more attention. So the moment that higher priority task becomes ready, it will automatically be allowed to run. Okay, so of course this can cause another issue, which is what we call the priority inversion. Okay, so what is priority inversion? Okay, so if priority inversion is where when one lower priority task blocks a higher priority task. Okay, so how is this possible? Okay, how is this possible? So let's look at this situation here where task one is running. So you can think of task one as lower priority and task 2 as higher priority. So task 1 is first running and it acquires a shared resource. Okay, so it acquires a shared resource. It could be locking a mutex, all right? Okay, so let's think of it as locking a mutex. Okay, so in this case, you lock the mutex. Okay, do a mutex lock, and after you lock the mutex, at this point of time here, there is a context switch. Okay, and in the context switch, what happens? You switch to the higher priority task. So the higher priority task now is starting to run from this time over here. Okay, and while the higher priority task is running, at some point of time, it tries to lock the same mutex. So this is R. So in this case, it also tries to lock R. Well, what happens? The task or the mutex R was already locked, okay, by the lower priority task. All right, so since it has already been locked by the lower priority task, the higher priority task now needs to give up the CPU, and now you transition back to allow the lower priority task to run. Okay, so you can see that this duration here, this T over here, is the duration of what we call the priority inversion. Why? Because during this time T, a lower priority task is actually blocking a higher priority task. Okay, it's blocking a higher priority task until the point of time when I release. So when I release the resource, then what happens? Then only the higher priority task can acquire it, okay, and get to run. Okay, and then eventually it will also release the resource, and then both the tasks can finish. Okay, so the critical thing is this duration over here. Okay, where we say that there is actually a priority inversion happening because a shared resource was locked earlier on by a lower priority task. So the higher priority task is now forced to wait. Okay, now this is what we call a bounded priority inversion. Why is it bounded? Because we are bounded by this time here T. So the time duration that we have to wait for the lower priority task to run and release the resource, that is the bounded time. Okay, so we know that this is the maximum amount of time that we have to wait before it can actually, the higher priority task can resume. But now there is another worst case to this, which is what we call the unbounded. Okay, the unbounded is the same situation, all right, where what is going to happen is, in this case, the lower priority task and higher priority task, but now you have a medium priority task. Okay, so in the medium priority task, what happens? So in this case, you can see that a low priority task is running. It gets, it acquires a mutex. And after it acquires the mutex, okay, at some point of time, there is a context switch and you start running the medium priority task. Then again, at some point of time, there's a context switch and you run the high priority task. But in between, while you're running a high priority task, you try to acquire the resource. Now, when you try to acquire the resource, it was already blocked here, okay, by the lower priority task. So since it's already blocked by the lower priority task, what happens? You are forced to go to the block state. So the high priority task is now blocked. But when it gets blocked, what happens? The lower priority task doesn't get a chance to run yet because there is still another medium priority task. So this medium priority task must first run until a point of time when it gives up the CPU. Okay, and then the lower priority task can then resume and release the resource, which can then allow the high priority task to acquire the resource. And this can be even more worse if you have many tasks in what we call the medium level priority, correct? M1, M2, M3, and so on. So this thing can go on, and this duration here can stretch very, very long, correct? If there are many tasks that are considered medium priority, they keep coming in and preventing the lower priority tasks from giving it a chance to run and release the mutex or the shared resource. Okay, so this is what we call unbounded because we really do not know how long we will end up waiting before the lower priority task can finally run and release that resource. Okay, so this is a real issue, correct? A real issue that can upend your system. Okay, because your high priority task, which is you allocated as high priority because it is important, but now it is ending up waiting for everybody else to finish, okay, before it can run. So how do we go about resolving this? Okay, so the good part is this can actually be handled by the OS itself in the background. So we do not need to worry about it, but we just need to understand what it's going to do for us. Okay, and the concept is what we call priority inheritance. Okay, so RTX also employs it, and many other RTOS out there also employs it. So when you say priority inheritance, now what happens here is you can see that when the point of time when task 3 tries to block the resource or tries to acquire the resource, and then it realizes, okay, the OS realizes that task 3 cannot carry on because the resource is held by a lower priority task 1. So at that point of time, what happens is the OS will temporarily raise the priority of the low priority task. Okay, so it will temporarily make T1 to be the same priority level as T3. So that is why the moment T3 gets blocked here, you can see that T2 doesn't run. It is the T1 that actually gets to run. Okay, so when T1 gets a chance to run, it will then be able to finish off whatever it was until the point of time where it releases the resource. Okay, the moment it releases the resource, okay, then it assumes its original priority. So it comes back down to the task 1 priority after that. So why is this able to solve the problem? Because now I cut out all of this. Okay, all the in-between tasks or the middle priority tasks will no longer interfere with this. Okay, so the moment the block comes in, I will raise my priority and I will allow the lower priority task that is holding the mutex to run, release the mutex so that the high priority task can now acquire it and finish up, okay, the critical activity. So that is the way we can solve this, and this is managed by the OS. We don't need to do anything. There's another uh, alternative way of solving it, which is what we call priority ceiling. So some OS employ priority inheritance, some may employ priority ceiling. Now in priority ceiling, the same concept, only thing is the lower priority thread is raised the moment it acquires the resource. The moment it acquires the resource. That means at this point of time, it is already raised up. Okay, because the OS will see which are the resources that are shared between tasks of different priority. So the moment a lower priority task acquires a shared resource, that task priority will automatically be raised to match that of the higher priority task. Okay, so that is the idea behind it, but it's the same concept of temporarily changing the priority. Okay, so in PCP, you will always raise the priority regardless of whether the higher priority task is blocked or not. Okay, so in PIP, you only raise the priority when a situation like this happens. That means a high priority task is blocked, okay, and it cannot carry on because the low priority task has already acquired the resource. Okay, in PCP, you don't wait for the block. The moment the resource is acquired, you straight away raise the priority. Okay, but they both help to solve this priority inheritance issue. Okay, it's just two different approaches to it. Okay, so in general, RTX scheduling uses what we call the round robin preemptive. Okay, and why round robin? Because tasks of the same priority go through round robin, but at the same time, the preemptive nature allows anything that is higher priority to automatically take over and run the CPU. Okay, so these scheduling things I think we have already discussed before. Okay, so just some admin matters. Okay, so this Friday I will be at the lab. Okay, but only in the morning part, so around 9:30 till 11:30. All right, so if you have anything that you want to consult me regarding the project or any discussions you want to have, you can come during that time. Okay, so I have to apologize, I'm not able to make it in the afternoon. Okay, so this is the slot that I can come. All right, so this Friday morning I'll be there. So if you wish to discuss anything about your ideas or any issues with your project, you're free to come at that time and meet me in the lab. Okay, so let's go for a break now. Now it's 11 o'clock. Okay, so let's go for a 10 minutes break. So 11:10 when we come back, I will go through the demo, okay, on the semaphore usage, okay, that you will uh, get to try out this Friday in the lab. Okay, so let's go for a break. Okay, I'll see you back here at 11:10. Okay. Okay, so let's look at the code that we have here. Okay, so before that, there was a question just now on the chat about the tasks, all right, the number of tasks that we can create. So in the requirement, I only specified a minimum of 4 tasks, all right, but there's no limit on how many tasks you want to create, all right. You can create as many tasks as you feel necessary to manage all the things you want to do, all right. The only reason why I put a minimum is so that you don't learn OS and then go and write one and then you write the whole project in one task, okay, without any multitasking, correct? So then it defeats the whole purpose. All right, so just to make sure that you think in that multi-threaded concept, all right, I put in a minimum of 4 tasks, but you are free to add in more tasks, okay, as long as you feel that it's necessary. All right, so let's look at the example that we're going to be doing in the lab. So this week's lab is about semaphores, and I'm going to link it up with also one of the activities for your project. Okay, so in the project, you're supposed to take the information coming in through a serial interrupt, and then from there relay that information to the task. Correct. So you have a T-brain task, and then you have other tasks that will then process this information. So I'm going to show you one way in which you can implement that uh, flow. That means how do you make sure that the task starts processing the information the moment a new data packet comes in. All right, so that is what you're going to be doing in the lab, and we're going to look at it now. Okay, so in the lab manual, okay, the first thing is we're going to create a normal uh, semaphore. So if you look at OS semaphore new, okay, okay, so if you open up your RTS documentation, when you call OS semaphore new, you have 2 parameters or 3 parameters. The third attribute usually we put as null. The first 2 is the max count and initial count. Okay, so in our case, what we're going to be doing is we are going to be running it as or we're going to initialize the max count as 1 and initial count as 1. Okay, so that is the semaphore. Now, once the semaphore has been created, all right, though here I have LED red thread and LED green thread. Okay, so both of them do the same thing. They acquire, they release. Same thing here, they acquire and they release. Okay, so if I were to run the code now, okay, so I think that it be no surprise that it will be as such, correct? That means you have red blinking and green blinking. Okay, so maybe I will go to debug mode and run one more time. Okay, so if I were to run the code now, you will see that it is red followed by green. So the behavior is very similar to what we saw for Mutex, correct? Why? Because in this case, the semaphore initial count is 1. All right, so it behaves as a binary semaphore. So the task acquires it, releases it, and so on. So when the red task acquires it, okay, it is going to control the LED. So when the other task tries to acquire it, okay, so if I were to draw the timing diagram here, okay, so I have a red LED thread and then the green LED thread. Okay, so what is happening is the very first time the LED run, okay, it will call OS, okay, sem acquire. So when it calls sem acquire, it acquires the resource and then it goes ahead to on the LED, switch on the LED. So of course, because of the context switching that is happening, so this is originally in the ready state, but the context switching will allow us to switch over to the green thread. Okay, so when I switch over to the green thread, then green thread will run, and the first thing it will do is it also tries to say OS sem acquire. Okay, but since the semaphore count, okay, semaphore initial count is 1, all right, moment I acquire it, it becomes 0. All right, so when sem acquire tries to run in the green thread, it will see that the count is 0, so the OS will automatically put this into the block state. Okay, you go to the block state, okay, until the point of time when your red thread finishes the loop. Okay, so if you look at the code here, you're finishing the LED on off, and then only it releases the semaphore. Okay, so when it releases the semaphore over here, okay, when it releases the semaphore, then you allow the OS will allocate the semaphore to the green thread. So the count is still 0. The count is still 0. Only thing is from the block state, it has now become ready. Okay, then again, because of the then when it becomes ready, what happens? Okay, so over here, of course, you can see that in the loop, the first thing that we do is the moment I release, I try to get back the semaphore. Okay, but I cannot get back the semaphore because the moment I release the semaphore, it went to green thread. Okay, so green thread has now acquired the semaphore. So even though I may call OSM, okay, acquire immediately after that, but there was already a task waiting for it, which was the green task, okay, the green thread. So now this one will go to a block state. Okay, and this one will now be able to transition to the run state. Okay, so this is on, okay, then off over here. So the same thing will now happen here for the green thread. So now the green thread is able to carry on. So it will on, then off, release the semaphore, and when you release the semaphore, this task here was waiting for the semaphore. So it'll automatically be allocated back to or allocated to the red thread, and red thread can carry on after that. Okay, so the semaphore is continuously being passed from the red thread to the green thread. Okay, and each time when one task has the semaphore, it is able to control the LED until it releases. But the moment it releases, there's always another task, the other task that is waiting for it. So it's automatically allocated to the next task. Okay, so that is basically how or why this is behaving in this manner over here. Okay, let me see where is the so the red LED and green LED. Okay, so any questions on this first demo? Anybody wants to ask anything? Okay, so if there are no questions on this, then let's just okay, okay, so when OS wait forever is 0, like I said, if your OS wait forever is 0, then what happens? That means you will proceed even without getting the semaphore. All right. So let's try this. Maybe OS M4 acquire here. Okay, let me do this. Okay, so in this case, LED green thread, I say semaphore acquire my sem 0. Okay, so what will happen? That means I'm telling the OS that I want the semaphore, but I don't want to wait for the semaphore. Okay, I don't want to wait for the semaphore. That means regardless of whether I get or I don't get, I will still proceed. All right, that means I will still be able to carry on controlling the LED. Okay, so if you run this, okay, effectively both the tasks. Okay, so let's see what happens. Let's see what happens. Okay, so as you can see, both the tasks are running together at the same time. Yeah. Okay, so it's quite bright, but it's basically yellow LED. All right, so it's similar to not having the semaphore at all for the green thread, because it is going ahead to control the shared resource even without the without acquiring the semaphore. Okay, so rightfully, if your code, if you want to put a timeout of 0, okay, what you need to do is in your code you need to put in switch case or if else statements to manage how the behavior should be if I get a semaphore, or and what do I do if I don't get a semaphore. In this case, we are not doing that, so it is still carrying on to do the LED control, even though the wait forever is replaced with 0. Okay. Now, how about if I change this? If I don't release the semaphore. Okay, so the green thread already acquired a semaphore. Correct. The red LED thread will acquire and release. Green LED thread will acquire, okay, but again is wait forever, but it will not release the semaphore. Okay, so what what do you think will happen? Okay, so you can put your responses in the poll. Okay, so let me show you the code again. So the red LED thread, no change. It acquire, control, and release. So no change with that. Only the green LED thread, there's a change, and the change is I acquire, but I do not release. So let me build the code. Okay, so let me end the poll. Okay, about 82% have voted. Okay, so it's quite close. So one option is green LED keeps blinking, and the other one is red LED 1 second, green LED 1 second, and stop. Okay, so the rest of you have also have other thoughts in your mind. So let's just see what happens and then analyze the results. Okay. Okay, so again, let's look at the code first. So the red LED, there is no change. Green LED acquires, okay, with wait forever, but it does not release the semaphore. All right, so let's run. So red, green, and that's it. Okay, one time red, one time green, and that's it, nothing else. No more LED. Okay, so why is that so? Okay, so let's again look at the timing diagram here. So we have a red LED. Okay, we have a green LED. Okay, so the red LED is created first. I mean, the thread is created first, so it is the first one to run. Correct. So when it runs, what will it do? It will take OS SAM acquire. Correct. So originally, your count is the Semaphore count is 1. Once it acquire, the Semaphore count becomes 0. Correct. And then what will it do? It will say on. Okay. So of course, in between, somewhere along the way, your green LED thread might try to run. Okay. So actually coming back here, your thread, again, as you can see, when you will switch over to green and you will run Semaphore acquire, we do not know, correct? Because of the context switching between equal priority tasks. So at some point of time, there could be some context switch over here. So originally it was ready, correct? But then when you context switch over, it tried to do a SAM acquire in the first case. But since the acquire, I mean the SAM is still 0, it goes to a block state. And then eventually, when you come back to red, okay, you can on, you can off. Okay, and after that, what do? You release. Alright, you finish already, you say OSM release. Okay, so when you OSM release, same as before, there is already somebody in the queue. The green task is already in the queue waiting for the semaphore, which means that once I call release, this semaphore count is still 0. Okay, it's just that it's automatically allocated here. So this task from block state can now become ready. Okay, so it's going to carry on in the ready state. Okay, and then when this task here calls the next SAM acquire, the semaphore count is still 0, so it will go to a block state. All right, and once it goes to a block state, okay, or timeout, whichever happens, you will be able to come back here, and this will be able to run. So when it runs, what happens? Your SAM acquire has already been allocated because the semaphore has already been allocated by the by the OS. So it can run. So what will it do? It will do the on, okay? It will do the off, okay? And after you do the on and off, what happens? Okay, it does not release the semaphore. Correct? It does not release the semaphore. Okay, so since it does not release the semaphore, okay, it will go back to the loop. So in the beginning of the loop, what happens? You call OS SAM acquire, correct? That's the first thing you do in the beginning of the loop. Okay, so since I call OS SAM acquire again, but the current semaphore count is still 0 because nobody has released it. Okay, so since nobody has released it, the count is still 0. So what will happen? I'll go to a block state. And red task also is still in the block state because it is also not able to get any semaphore. Okay, so from this point onwards, both the tasks are indefinitely blocked. Okay, so that is why you do not see any LED blinking after that. It's only one time each. Okay, so again, it comes back to the concept of the OS, how the OS behaves. All right, as far as the OS is concerned, whenever I call OS SAM acquire means I want to acquire a resource. Okay, it does not think that that green thread is the one that acquired the resource the last time round. So if I try to call it again, should be fine because I already have it. No, it does not think that way. Okay, because again, the semaphore is tied to resources. It could be a case, all right, in your code, maybe that you want 2 resources. Okay, the semaphore is to manage 2 resources, and you want, you have a task that you need both the resources to fulfill that task. Okay, so for example, okay, if you go back to the notes just now where we talk about the 2 ADC, okay, it could be a situation where maybe your IR sensor is connected and at the same time you have your temperature sensor, and you want to do TIR and TTemp at the same time. Okay, or you have another task called data that wants to run or activate both of these tasks at the same time. Okay, so in order for T data to run, it needs to have two ADC modules. So maybe the T data might acquire both the semaphores first. All right, and then allocate TIR and TTemp to perform the action. Okay, so you can have a task where the way you design it is I need both these resources, then I can carry on with my task because my task requires these two resources. Okay, so as far as the OS is concerned, you will look at it from the perspective that when I call OS semaphore acquire, this task wants to acquire a semaphore. It doesn't matter that I already acquired one earlier. It wants to get one, can I allocate it? If it's available, you will allocate and you will run. If it's not available, then the allocation will give me an error message, so I'll go to a block state. Okay, so that is how the OS will behave. All right, so that is why even though the green thread is the one that acquired it last, the next call is considered a fresh new call. Okay, for the semaphore, and since there are no more semaphores available, you will go to a block state. All right. Okay, so before I go to the next demo, any questions on this? Okay, so in the lab demo, okay, so these are things you can try out in the lab. All right. Now the last one is what we are going to do is we are going to integrate the push button switch. Okay, so and when we integrate the push button switch, we are going to create the semaphore with a max count of 1 but initial value of 0. Okay, max count of 1, initial value of 0. That means initially there is no semaphore. All right, so and both the tasks are written such that they will acquire the semaphore. Okay, and when they acquire the semaphore, then they can proceed to control the LED. Similarly over here, they acquire and then they can control. So now let's look at this code first and understand what is happening. All right, so now I have two threads, red thread and I have green thread, but now I have created a semaphore with initial count of 0. Okay, initial count of 0. So red thread will run first, okay, and when it runs, okay, you will call OS sem acquire. Correct, that's the first thing you will try to do, but semaphore is 0. So what will happen? It will go to a block state. Okay, and since it goes to a block state, okay, it will allow a contact switch also at the same time. And your green thread, which was originally in the ready state, will go to a run. And then over here, what will I do? I'll do the same thing. I'll call OS sem acquire. And again, no semaphore is available, so I'll go to a block state. Okay, so when you do this part in the lab, you will see that when the system start up, both of the tasks will try to acquire the semaphore and both of them will go to block state because semaphore is 0. So where does the semaphore come from? Okay, so the semaphore is going to come, okay, from the interrupt. Okay, so what you're going to do is you're going to use the code that you have done before where you have the push button switch tied to the port D pin, and you're going to configure all you can just copy over the code you've done before. So in the past, when we press the switch, what do? We control the LED. Correct, we can control the LED in the IRQ handler. All right, now what we are going to do is instead of controlling an LED, we are going to release a semaphore. Okay, we're going to release the semaphore in the IRQ handler. So what is going to happen? So we do not know when the switch is going to be pressed. Okay, so at some point of time, okay, let's say over here, I press the switch. When I press the switch, what will happen? I will release a semaphore. So when I release a semaphore, so this will release semaphore, correct? Okay, so when this interrupt happens, okay, when this interrupt happens, we do not know when, but it will release a semaphore, which means that right now in the queue, in the semaphore queue, okay, you have red thread followed by the green thread. Okay, so when this semaphore is released, it will automatically allocate to the first task in the queue, which is the red. So this semaphore will automatically be allocated here, which will allow it to unblock and go to a ready state. So once it goes to a ready state, it can now go ahead and control the LED. So it does the on, off, everything. But the moment it does the on and off, okay, the moment it does the on and off, it goes back to the top of the loop, okay, and tries to acquire again. Okay, tries to acquire again. So it will on off, and then it will call another OSM acquire. Okay, so when after allocate, it will call again, so it will come here. It will come after green. Because now red has already been gone from the queue, so green is in the top and red is now coming again next. All right, similarly, when I press the switch one more time, when I press the switch one more time, again, I will release. Okay, and then it will allocate to whoever is next in the queue, which is the green. So it will now come to the green, and green will allow, or green will become ready. Okay, and then from there you can go to run, and then you do the same thing. You do the on, okay, you do the off, and then you go back to the top of the queue. Okay, and in the top of the queue, you will again call OSM acquire, and the same thing will start again. So it will come again over here, green. Okay, so what is happening is the switch is now the main sort of block that releases semaphores. All right, and as and when a semaphore is released, the task that is now waiting in the queue will be able to acquire the semaphore. Okay, we'll be able to acquire the semaphore. So let's see this in action. So let me build the code. Okay, so now I've started to run. As you can see, the moment I run, nothing happens. Okay, no LED is blinking because currently what is happening is both the tasks are in the block state, waiting for me to initiate a push button. Okay, so let me press the button once. Okay, so you can see that when I press the button once, okay, it released the semaphore, which allowed the red LED task to unblock and carry on. Okay, and now red is joined the queue, but now the front task in the queue waiting for semaphore is green. So if I press one more time, the green will be activated and so on. So you can see that you continuously switch between red and green. Okay, so that is what you will observe, okay, when you run this in your lab. Okay, and why is this? And this gives you one way of now controlling the flow, correct? That means when the data comes in through the serial port, okay, you can do something similar, correct? So in your serial interrupt, after you receive the data, you can now use semaphore as a means to activate the first task that is supposed to process this data. Okay, and then the rest of the things can carry on. All right. So this is one way of doing it. All right. But you can try it out. Okay. But in the next few lectures, we will be learning other techniques as well. Okay. So there is still thread flags. There's still event flags, which are also and there's also message queue. Okay. So we are going to be looking at these other concepts. Okay, in the subsequent lectures for you to try out. Okay. So you're learning different techniques, different tools, and then you can decide which of these you want to use in your final architecture. Okay, if you want to use message queues and do it, it's fine. You want to use event flags and do it, you want to have a mix of everything, is also fine. Okay, so how different tasks talk to each other, how they synchronize. Okay, there are many ways of doing it. Okay, so you're learning different ways, and then along the way you decide, okay, which is the best way that you think is suitable for your idea. Okay, so the port D, the reason why I put a delay here is just because of the switch debouncing. Okay, if you don't put a delay, then you will end up sending having many interrupts. So many semaphores will be released. All right, and then that so when you have that, you might see that red and then even green, then you might see yellow color. Okay, so this is just to handle the debouncing issue. Okay, so of course, if you click on it, okay, if you click on the button many times, all right, and you release a semaphore, okay, what will happen is if you try to release beyond what you have, okay, in a situation of a task context, you can block the task. All right, in the situation of an interrupt, it will just return an error. That means it cannot update the semaphore anymore because you already hit the max count. Okay, so the behavior will depend on how you want to make use of the error message that comes back. Okay, so these are things you can read up also on your documentation to see what will happen if I exceed the count. All right, so there will always be some default behavior and probably some way of changing it if you want to play with the error messages that you get back. Okay, same thing like mutex lock. All right, if you lock and you cannot get the lock, you don't want to be blocked, you can use the error message as a way to carry on, okay, by not waiting forever. Right, similarly for OS Semaphore release, there is also different ways of what will happen if my semaphore count goes beyond the max count. Okay, so yeah, so this is basically what you will try out in your lab, okay, and you can see for yourself. All right, so when you try all this, I think the important thing is for you to understand how this can be used as a way to develop some part of your architecture. Right? If I want one task and another task to synchronize in some way, semaphore is one mechanism. Right? If I have shared resources that different tasks are using, you can use semaphore to control that shared resource. If you have critical section of the code, some shared buffer memory that you want different tasks to access, you can use Mutex. So think of how you will apply this when you are developing your code, okay, for the project. All right, so that's all I have for today. Okay, so we have covered basically the topic on the concurrency of Mutex and Semaphore. All right, and some recap of OS and the kernel behavior. All right, so the next few topics are basically a message passing, all right, and event flag and thread flag. So these are ways in which you can send data from one task to another task while you also synchronize the behavior at the same time. All right, so these are other techniques you will learn in the next lecture, and then after that we will just wrap up with a few more aspects of OS that we need to look at, and then we are more or less done with the lecture content, and we can just focus on the project. All right, so that's all I have. If you have any questions, you can ask me. If not, thank you very much. Okay, and then Friday morning, okay, those who are coming to the lab, you can consult me there if you have anything you want to ask me. Okay, so thank you very much. Okay, and I will see you all on Friday.